This is the BMP390, a digital barometric pressure sensor by Bosch. It's the same one I'm using on a flight controller, and today we are writing a platform-independent C++ driver for it. We'll start by exploring the datasheet, identify the features of interest, lay out the architecture of the driver. Then we'll work through the implementation, and by the end of this video, we'll have a working driver that can read pressure, temperature, and use the data to estimate altitude. Before diving into the code, we need to be clear about what the driver is and what it isn't. The BMP390 has a lot of features, but that does not necessarily mean we require them all. That said, there are 4 key requirements that the driver must fulfill. It should support both I2C and SPI interface and extract the pressure and temperature data. But this does not mean we should restrict the features to just these. To uncover what's being left, we must dive into the datasheet. I won't read through each and every line, but instead highlight the area of interest. To start with, the BMP390 has 3 power modes: sleep, forced and normal mode. Each selected by writing to the mode bits in the power control register. After a power up or a soft reset, the sensor enters sleep mode, wherein no measurements are performed. To detect if the chip has powered up or executed a soft reset, the power detected bit is set to 1 in the event register. The force mode is selected by either writing 01 or 10 to the mode bits in the power control register. In force mode, a single measurement is performed. After performing a single measurement, the sensor goes back to sleep mode. For the next measurement, the force mode has to be reselected by writing to the mode bits in the power control register. The third mode is the normal mode. The normal mode is selected by writing 11 to the mode bits in the power control register. In this mode, the sensor continuously measures the temperature and pressure at a measurement rate defined by the ODR select bits in the ODR register. The sampling period of the measurement is given by this formula. To measure the pressure, press EN bit in the power control register must be enabled. Additionally, it offers oversampling to reduce noise and increase the output resolution. The oversampling parameters of pressure are set by writing to the OSR-P bits in the OSR settings. Moving on, we have the temperature measurement. It is enabled by writing to the temp EN bit in the power control register. Just like the pressure measurement, it offers oversampling to increase the output resolution and decrease the noise, configured by the OSR-T bits in the OSR register. Now it may seem irrelevant to focus on temperature, but it is quite important as it is something used to compensate the pressure readings. I'll talk about it later in the video. There is a lot more on the table and we are going to cover them all. But how about we put into use what we have gathered so far? I'll start by creating a folder with the name BMP390. Inside this folder, I'll create 2 folders, one labeled INC for include files and the other has SRC for source file. I'll add the BMP390 directory into CubeIDE as a link and update my include part settings in the project menu. Now, I'll create some source and include files. First is a header file named bmp390.hpp. This will contain the BMP390 class and the required functions to configure and read data. I like to store the register definitions and bit fields in a separate header file. In this case, it is bmp390-rec.hpp. Now in the source folder, I'll create the bmp390.cpp file. This will contain all the function definition. Can't forget to include the bmp390.hpp file. I'll start by adding the register definitions and the bit fields. Now I like to organize the register definitions and their fields in a namespace. Generally, people use #define and cast the value into the required data type, but CPP offers the const_expr keyword to allow for compile type evaluation where possible. Therefore, the const_expr keyword along with the uint8 type is used for the register definitions. This process is quite straightforward. Just copy the register names and assign them their addresses from the datasheet. I usually use ChatGPT for this. I send it the pictures of the register map and have it extracted into a C or CPP file. But because BMP390 has so few registers, I did not bother doing so this time. Alright, the register addresses are done. Oh, I almost forgot the reg_ prefix before the register names, but it is really easy to add. This looks good. Alright, time for the bit fields. I'll go ahead and write some of them. Here I wrote a few bit field definitions. The way I like to write them is by prefixing the bit fields with the register name. Additionally, some bit fields like mode, OSR, ODR occupy more than one bit field. Therefore, underscore 0, 1, 2 or 3 suffixes are used based on their size. There we go, everything's complete. Looking back at it now, I should have used ChatGPT, it would have been a lot quicker. But nevertheless, I want to bring your attention to these two registers, the chip ID and the rev ID. They are read-only and have a fixed value of 0x60 and 0x01 respectively. They are usually read on startup to verify if the device is working and present. Therefore, we'll add them to our code like so. There are other stuff left such as adding enums for power modes, oversampling and whatnot, but we'll leave them for later. Let's go ahead and create the BMP390 class. But first, we'll have to create another file called bmp390-4.hpp. This will contain the return types for our functions. But why can't we directly use types like int or float? Well, this is because it is a platform-independent library. We could be using it as to HAL framework where the return type for function is HAL status, or we could be using it with the Arduino framework with a different return type. So instead of changing the return types for the function across the files, we can just redefine them here in our code, before including the bmp390.hpp file. I have used uint8_t as the default value, but you will have to change it depending on your platform. Although, you can use it as it is, and it will work just as well. Finally, we move on to creating the class. I name the class as BMP390 and add the private and public labels. To configure the barometer, we need some read and write functions, but we cannot determine the implementation as it will depend on platforms such as ST's HAL or the Arduino framework. Therefore, we will utilize function pointers. The first parameter is a void pointer to an interface object. What is an interface object here? When we use I2C or SPI in STM32 or Arduino framework, we use objects like hi2c or wire belonging to hi2c handle typedef struct or the wire class. The address of hi2c or the wire object is what the h interface pointer points to. When implementing the read or write function, the h interface pointer is cast into the appropriate type, that is hi2c handle typedef or wire depending on the platform. The rest of the parameters are self-explanatory. Chip address is the I2C address, reg is the register to read from, buff is the place to register contents will be stored, and len is the number of bytes to read. We'll create a duplicate for the write function and change the name. Now we can add the read and write function pointers into the private section, as well as the h interface pointer. Additionally, I'll add a delay function. I might remove it if it is not utilized. And the chip address variable to store the I2C address if in case we are using I2C communication. In the constructor, we simply assign the h interface read, write and delay functions to the h interface read, write and delay ms function pointers. There's a small mistake here. Both the namespace and the class have the same name, so I'll change the namespace name to lowercase. The BMP390 can operate in both SPI and I2C mode, which is enabled by setting the CSB pin either high or low. When in I2C mode, the I2C address is set by the state of the SDO pin. So with this knowledge, we'll create an init function which sets the I2C address based on the SDO pin state if CSB is set high. The function pointer returns void and takes two arguments, first the CSB pin state and second the SDO pin state. If CSB is high, check the SDO pin state. If it is high, set the chip address to 0x77, else 0x76. Small correction here, the chip address should be initialized to 0 in the constructor. Few moments ago, we discussed about the chip ID and the rev ID registers. So using them, we are going to create a function to check if the device is present. The return type is bmp390_ret_type. The name is IsPresent and takes no argument. We'll use three variables here, one to store the chip ID, another for the rev ID, and lastly the return code, which is set to failure by default. We are first going to read the chip ID reg and store it into the chip ID. If the read is successful, we'll proceed to read the rev ID into the rev ID. Lastly, if the read is successful, then we'll compare the value of chip ID and rev ID with the one defined in the namespace. If it is a match, we set red to success and return, else we return failure. Now, we can implement other functionalities such as changing power modes and all. But ever since I made this flight controller, not once have I tested it to see if the barometer is even functional. And with our IsPresent function ready, I think it is time we do that. To start with, we'll include the BMP390 header, and just above it, we'll define the return types to use the HAL status typedef enum. With this done, we'll have to create the read, write and delay functions for the barometer. I'll start with the read function. I'll name it BMP390_I2C read, and the parameters are the same one defined in the function pointers. In the body, we'll create a variable to store the return code and set it to HAL error. I'll use the HAL I2C memread blocking function to read the chip's register. The H interface pointer is cast into the I2C_handle typedef pointer. Dev address is the chip address. Mem address will be the register to read from, casted into uint16 type. Mem size is the size of the chip's register, which is 1 byte. Pdata is the pointer to the buffer. Size is the number of bytes to read, which is set by len. And lastly, I will set the timeout to 2 milliseconds for now. HAL status typedef has 4 return types, but I define only 3 in the BMP390 file. Therefore, if the return code is timeout, I will set it to HAL error. The write function is an exact replica of the read function, with the HAL I2C memread function being replaced with the HAL I2C memwrite function. Just a small correction, the variable for static cast should be surrounded by parentheses. The function declaration must be copied and pasted above the main function. Lastly, we'll create the delay function. I'll add the prototype over here, and then define the function over here. It will always return OK, and the H interface is cast into void type to avoid unused variable warning, or you can replace void star H interface with just void star. HAL delay function simply takes the delay argument and creates a delay. With this being done, we can create the BMP390 object. I'll name it baro and pass in the arguments. The reference to HI2C object should be casted into a void pointer. The BMP read, write and delay functions are passed as is. This is because the function name points to the starting address of the function. Another mistake here, the chip address should be right shifted by 1, as the 8-bit in an I2C address is used to indicate a read or write operation. Moreover, the BMP390 object should be placed after the read, write and delay function prototype. Compiling it, we see everything is okay. I went ahead and wrote the code to check for device presence. First, the peripherals are initialized. Then we set the I2C address using the init function. An array named str is created to store the string. In the while loop, we check if the barometer is present. If true, the string present is copied into str and printed through the virtual COM port. Else absent is printed. Okay, let's upload the code and open the serial monitor. There we go, it prints present. To get anything useful done with the barometer, we should be able to change its power mode. Therefore, we'll create a function for it. But first, we should create an enum to contain the power modes. I'll use enum class and name it power mode. The size of its content is 1 byte. The BMP supports 3 power modes and they are listed as so. In the class, we'll create the function called setPowerMode and it takes one argument of the type power mode. In the CPP file, we'll create the definition. But before this, I need to explain the methodology behind write operations. To change the power mode, the mode bits in the power control register must be changed. Suppose we want to switch to normal mode from force mode. We'll write 0x60 to the power control register. But this sets the temp en and press en bits to 0, that is disabling temperature and pressure measurement. Therefore, to mitigate this, we'll first read the power control register into a variable. Now we'll set only the mode bits, that is bit 4 and 5 to 0. Now we'll set the 4th and 5th bits to 1 using bitwise shift and OR operations. With this done, we can write the variable into the power control register without changing the temp en and press en bits. And this is the method that we are going to use when the contents of a register needs to be modified. Coming back to the set power mode function, I'll create a variable read to store the return code, another called PWR control set to 0 to store the contents of the controller register. Now, we'll read the contents of the PWR register into power control variable. I'll use a switch case statement to set the power mode. But first, the mode bits, that is 4th and 5th bits in the variable, must be set to 0. For force mode, the mode 0 or mode 1 bits needs to be set to 1. And for the normal mode, both the mode 0 and mode 1 bits are set to 1. Finally, we can write the value into the power control register of the BMP390, and the return code is assigned to ret. Just a small mistake here, I need to prefix the enums with the namespace names along with the scope resolution operator. Compiling everything, I see no error. In a similar manner, I'll create a function to toggle pressure and temperature measurement on or off. In the class, I'll declare a function with the name toggle pressure measurement, and it takes boolean as an argument. 1 means turn the measurement on and 0 means turn it off. Another one for temperature measurement, with the name changed to toggle temperature measurement. In the CPP file, I'll create a definition for toggle pressure measurement. I'll copy the body of the set power mode function and remove the unnecessary lines. Instead of the mode bits, the press en bits must be changed. If n is true, set press en to 1, else to 0. And then write the value to power control register. I'll copy the same function and rename it to temperature measurement. It seems that I made a mistake in the previous function. Instead of enabling pressure, I enabled temperature. So I simply change the temp en to press en. Compiling it, I see no errors. I forgot to discuss about it before, therefore I will tell you about the status register right now. It has 3 fields. Bit 6 indicates whether the temperature data is ready. Bit 5 is a pressure, and the 4th bit indicates if the chip is busy or not. The pressure and temperature data occupy 3 bytes each, and are stored in the registers data 0 to 2 for pressure and data 3 to 5 for temperature. To avoid corruption of data, it must be read in one go, rather than addressing each register individually. Continuously polling the register to check for available data is really inefficient. This is why the BMP390 offers interrupts, configured through the int control register. It offers configuring parameters such as type of output, output level, and whether the pin should be latched or generate a pulse. But the feature that I like the most is the inclusion of a IIR filter, that is a low-pass filter, to filter out noise caused by disturbances such as wind blowing over the sensor. This is quite useful as it helps to offload computation to the barometer rather than doing it on the microcontroller. To configure it, we must set an appropriate filter coefficient and write it to the config registers bit 1, 2, 3. Selecting an appropriate coefficient can be tough, but Bosch has already done the work for us by providing a set of coefficients based on our use case. Besides this, it also offers a FiFo or a buffer to store a bunch of data on the chip and read them at a later stage. But because I plan to use it on a quadcopter, I want to read the data as soon as it is available. Therefore, this is a feature that I will not be implementing in my driver. Now we can move on to implementing the rest of the features in a similar manner as we did for the previous functions, which involves creating enums where applicable and writing the functions. To avoid repetitions, I'll go ahead and create functions to configure oversampling, output data rate, check for data ready status, and reading the data. It took me some time, but here are all the functions, starting from oversampling to output data rate to setting up IIR filter and configuring the interrupt pin and interrupt sources. But some of you might have noticed there are no functions to read the temperature and pressure data. Well, this is because we are yet to tackle the last piece of the puzzle, which is about compensating the readings. No two sensors have an identical sensing element. Therefore, to receive accurate physical values, the readings have to be compensated. Thankfully, Bosch has already done the work for us and stored the compensation values into the non-volatile memory of the BMP390. The non-volatile memory starts from the memory address 0x31 to 0x45. But how do we use these values to actually compensate the readings? Well, thanks again to Bosch because they even provide an example code to do that. First, the calibration coefficients must be read and converted into floating point numbers by using the shown conversion formula. Once this is done, we need to compensate the temperature as shown in the example code. This is because the compensated temperature along with the coefficients in the NVM is used to compensate the pressure. In the example code, they take the raw pressure values and temperature readings and convert them into Celsius or in Pascal. In the code, I created a function called readNVM to read the non-volatile memory. Since the parameters need to be converted into floats and stored for future use, I created some private variables which are all set to 0 in the constructor. In the function, I read the NVM data into the NVM par array. Some parameters are 1 byte long, while others are 2 bytes in length. Not only this, but some of them are unsigned while others are signed. So they are arranged accordingly and converted into the required type. The parameters need to be converted into float. Using the given conversion formula, I converted them into floats and stored them into the respective par T1 to par 11 variables. To compensate the temperature, I create a function called compensated temperature, which takes the raw ADC readings as the argument and returns the compensated temperature. The implementation is copied directly from the datasheet, with changes made only to the variable names. Initially, I made the return type to be BMP390_ret_type, which should be changed to float. After renaming the variables and removing the unnecessary lines, our function is ready. Next, I will create functions to compensate the pressure. It takes the reading from the barometer as well as the compensated temperature to return the compensated pressure readings. The implementation is taken directly from the datasheet and the variable names are changed as per the ones defined in our class. Here is the complete function, which is missing the compensated temperature argument, so I'll add it now. This does it for the compensation. Now let's look at the function for retrieving the temperature data and compensating it. I have named it GetTemperature, and it takes a reference to a float to store the compensated temperature. The implementation is really simple. Just read the data registers from data 3 to data 5 for temperature. Convert them into unsigned int and pass it to the compensate temperature function. The function for pressure measurement differs slightly from the temperature function, as it combines both temperature and pressure measurement into one. This is because the barometer can be operated as a standalone temperature sensor, in which case the getTemperature function is used. While it can be used as a standalone pressure sensor, it is not advised to do so, as the compensation for pressure requires the compensated temperature value. Therefore, both functionalities have been combined into one to avoid reading data from different cycles. The function is named getTemperature and pressure and takes a reference to a temperature and a pressure variable to store the compensated temperature and pressure. First, the data registers from data 0 to 5 are read into raw data and separated into uncompensated temperature and pressure. Next, the temperature is compensated, and the compensated temperature along with the uncompensated pressure reading is passed to compensate pressure function to get the compensated pressure reading. This marks the end of our driver development journey. I have documented the function in Doxygen style. I had ChatGPT write the documentation, which I later reviewed and modified. Now let's actually put the code to use and extract some temperature and pressure measurement from the sensor. First, the microcontroller's peripheral are initialized, and then I wait for around 20 milliseconds before checking for the barometer's presence. Next, the NVM is read. If the read is successful, we configure the power mode oversampling output data rate IRR filter coefficient based on the recommended settings. Then the interrupt source is set up, and lastly the temperature and pressure measurements are enabled. You may have noticed a difference here, which is the pressure and temperature toggle functions have been combined into one. This is done so that they can be enabled or disabled in sync. Additionally, between each step, I check if the baro is busy or not. In the while loop, I read the interrupt pin to detect a transition from low to high. This is not the correct way to do this. An interrupt should be set up to trigger on the rising edge of the pin to read the data. However, this code is meant to demonstrate the functionality of the code. Therefore, I did not bother with setting up an interrupt. Nevertheless, when a transition is detected, the temperature and pressure readings are read and transmitted through the virtual COM port. Let's upload the code and see how well it performs. When the sensor is first powered up, you need to wait for a few seconds for the sensor's temperature to stabilize to get stable readings. This is the setup for the demonstration. The flight controller is placed inside a container. The container has a hole to pass the cable as well as allow airflow in and out of the container. This is done because when moving the sensor around, Fast moving air directly over the sensor can create low pressure regions, resulting in false measurement. Anyway, the temperature has stabilized. Lifting the sensor up, the pressure value decreases, and when it is brought back down, the pressure value increases. The pressure value fluctuates by about 1 or 1.5 pascals, and this is to be expected for the given sensor configuration and is mentioned in the table 10 of the datasheet. While we can measure the pressure, it does not tell us much about our altitude. To estimate the altitude, we can utilize this formula, which is applicable for altitude up to 11 km. The value for the constants R, LB, G0 and M are already provided, and we will substitute them into the equation and calculate the exponent value like so. HB is the height at sea level, which in our case is 0. TV is the standard temperature at sea level, which is 15 degrees Celsius or 288.15 Kelvin. PV is the pressure at sea level in pascals, which is 100,000-1325 pascals. And P is the pressure measured by the barometer. Solving and simplifying the equation, we get this, where P is the pressure reading in Pascal from our barometer and H is the altitude in meters. I made a function GetAltitude which takes a reference to our pressure readings in Pascal and returns the altitude in meters. In the code, I read the data as previously shown, but instead of printing the temperature and pressure, I print the estimated altitude in meters. Uploading the code and opening the serial monitor, we can see our altitude above mean sea level, which is around 88.75 meters. Let's see how accurate it is by lifting the sensor up by 30 centimeters and reading the results. The altitude has increased to about 89.05 meters, which translates to a difference of 30 centimeters. Perfect, although the readings are a bit noisy and fluctuates by about 10 centimeters. This is to be expected and is clearly stated in the datasheet as RMS noise for the given configuration. This means that measuring small changes, especially under 15 centimeters, is not possible with just the barometer alone. Therefore, to mitigate this, the readings are usually combined with an accelerometer to improve the accuracy. And this is what I will be covering in my next video. While this driver is available on my GitHub, I highly recommend that you write one from scratch. Most importantly, explore driver code by vendors such as Bosch or ST Microelectronics for their devices to learn how the industry writes their driver. Thank you for watching, and I'll see you in the next one.